And we are now recording. As usual, it takes me a little while to get the screen share set up. While I'm getting it set up, we only have 6 weeks left, folks. We're about the 2/3 way through the course, roughly 2/3 of the way finished. So we have 1, 2, 3, 4, 5, 6 weeks left. Okay. Again, it's still iffy whether I'm going to have the exam on the 23rd or not. I'll let you know hopefully later this week. Next week, there's a mini holiday in the middle of the week on the 22nd. It's a flex day, which means teachers and faculty and staff have to show up, but you folks don't. Okay. So I'll let you know if we're going to have the test here or push it back. Now, if I push the test back, it does not mean we're only going to do, chapter 4 stuff. If the most likely scenario is if I do push the test back, we're just going to keep going and do some of, chapter 5. I can't stop. We do have some buffer days at the end just in case I fall behind, but we'll see how it goes. Okay. I guess technically I'm a little bit behind because I want to do a little bit more in 4.3 and I'll try to get started with 4.4 today. Okay, so we're still on the topic of curve sketching, and yes, I realize a lot of these problems can get long, but that's par for the course, sort of. Okay, so you have to be ready for the possibility of super long problems. Now in the exam, I'll keep that in mind. So I realize you only have an hour or 50 minutes, and whatever I have to give you is quote unquote fair for that. Okay, so I'll do one more curve sketch, then introduce 4.4. Yeah, some of you just joined late. Go ahead and put your name in the chat and I'll get you for attendance a little bit later. 4.3, I was going to do 51 because it's a little bit unusual. Okay. And by the way, 4.5 is again more curve sketching. So we got curve sketching, and more curve sketching. So 4.3, a lot of curve sketching. 4.5 is a lot more curve sketching. Okay. Then 4.4 is something else called L'Hopital's, and we'll get to that starting today, hopefully. Okay. But 4.3, number 51. F of x is radical x squared minus 1 minus x. Okay. Before doing the complete analysis of it, there's some things that I need to show you about that. For instance, does this thing ever touch the x-axis, which means can y ever be 0? Let me show you over here. Suppose I set that equal to 0. Okay, so it's radical x squared plus 1 minus x equals 0. That was the original. Move over the x, square both sides. And this automatically can't happen. X squared plus 1 equals x squared. Okay. You can subtract x squared on both sides, you get 1 equals 0. But basically the statement is saying a number is equal to the number plus 1. That's impossible, right? Okay, so this thing never touches the x-axis. Okay, is it above or below the x-axis? Why don't I just plug in an easy number like a 0? What happens when you plug in 0? You get 1 minus 0. So this thing's always positive. Not readily evident, but it is always positive. So whatever the graph is, it's always above the x-axis, is what we're saying. Okay, so let's take the first and second derivatives as usual. So remember, this is like blah, blah, blah to the 1/2. So the derivative is 1/2 x squared plus 1 to the negative 1/2. That's negative 1/2. Times the derivative of the inside, which is 2x minus 1. Clean it up. X over radical, the 2's cancel out. X over radical x squared plus 1 minus 1. Second derivative, well, the derivative of that is 0, so don't even worry about it. And let me do the bottom first. That's easy. What is the square root of x squared plus 1 squared? That's just x squared plus 1. Now the hard part. Bottom times the derivative of the top. Derivative of the top is just 1, so you don't have to write it. Minus the top, which is x, times the derivative of the bottom. Derivative of the bottom is 1/2 x squared plus 1 to the negative 1/2 times the derivative of the inside, which is 2x. Okay, so clean that up. That's radical x squared. And let's see, what do I have over here? That 2 cancels that 2. I have x times another x, which is x squared. And that's a radical x squared plus 1 on the bottom of this, not the bottom of the entire fraction now, just the bottom of this expression right here. So it looks like this. Okay, so this looks pretty bad, but you can make it a lot better if you multiply top and bottom by radical x squared plus 1. It's a nice trick. Which makes the bottom now x squared plus 1 to the 1, x squared plus 1 to the half. That's x squared plus 1 to the 3 halves. And now, what is radical x squared plus 1 times itself? Just x squared plus 1. And then if you take this times this, these cancel out, so you just minus x squared. X squared cancels out x squared. So you have 1 over x squared plus 1 to the 3 halves. That's always greater than 0. Right? X squared plus 1 is already a positive quantity. Raises it to 3 halves, always greater than 0, no matter what. Okay. By the way, this thing has a domain all real numbers. There's no problem spot. Even though there's a square root, the thing underneath the square root cannot be negative, right? It's a square root of x squared plus 1. So the domain is all real numbers. This thing automatically is already concave up from negative infinity to infinity, which means all real numbers. It's never concave down, so there's no inflection points. So that part's easy. Okay. And there's no need to set this expression equal to 0. I already know it's always positive. So if it's always positive, the graph is always concave up. Now let's work on setting the first derivative equal to 0. X over radical x squared plus 1 minus 1 equals 0. That was my first derivative. Move the 1 over. Multiply both sides by radical x squared plus 1 to clear the fractions. And then I squared both sides. X squared equals x squared plus 1. The same thing, that can never happen. So what does that mean? The entire real number line is the same sign. I don't lay anything down, but you know how normally we put something on a real number line? Okay, there's nothing to lay down, but you can still plug in a number. You can plug in any number. So the number I decided to plug in was 0. 0 divided by that is 0. 0 minus 1, negative. Okay, so this graph is always decreasing. Okay, so f is decreasing from negative infinity to infinity, increasing nowhere, and there's no maximum, no minimum. Okay, then one other analysis that I wanted to show you is what happens in the end behavior, what happens when x approaches infinity or negative infinity. Okay, so let's go back to the original. When x approaches negative infinity, plug in negative a billion. This is a big positive. Minus a negative billion, that's a double negative. It's also a big positive. So if a big positive plus a big positive is big positive, y approaches infinity. So when x goes way out to the left, the graph goes to infinity. Okay. And then I want to know what happens when x approaches positive infinity, which is a little bit tougher. Okay. So I just look at this. This is considered infinity minus infinity, which means we don't know what happens. Right? You got a big number minus a big number. But we've played that game before. The way to get around that is to multiply top and bottom by the conjugate of this expression, right? So the conjugate is radical x squared plus 1 plus x, top and bottom. So the bottom is radical x squared plus 1. Let's see. Made a mistake. There shouldn't be a radical here. It actually doesn't change the answer. That shouldn't be there. Radical x squared plus 1 minus x, radical x squared plus 1 plus x. So that's like a squared minus b squared. The square of this is x squared plus 1. The square of this is x squared. And this is still radical x squared plus 1 plus x. I messed up, the square root shouldn't be there, but fortunately it didn't change the answer. Okay, that comes out to be 1. So if limit is x approaches infinity of 1 over radical x squared plus 1 plus x, no radical, although that wouldn't have mattered. So now if I plug in a super big number, this is big, whether I had the square root or not. Big plus big is big, and 1 over big is 0. Okay, so I have everything. I do have an intercept. When I plug in 0, I get 1, 0, 1. So here we are. The function is always positive, always above the x-axis, always decreasing, always concave up. So here we are. Always above the x-axis, always decreasing, always concave up. This side shoots up to an infinity, this side approaches 0. So this ride, if you were, this roller coaster always does the same thing. It just slides down like this. I guess I've seen slides like this also, right? Playground slides, they kind of go like that. And there we go. All right, so that's the last problem I was going to show you for now in 4.3. I may come back and do more, but I need to get started with 4.4. Let me do my focusing thing again for you. Give you all that. All right, so 4.4. Introducing 4.4. Okay, the topic is something called L'Hôpital's rule. It looks like L'Hospital's rule, like hospital, and it is. In fact, you spell it like hospital. Okay. I prefer the French pronunciation, L'Hôpital. It's a little bit easier to roll off the tongue than L'Hospital's rule. Okay, so the French way to say it, you know, I don't know how many of you know French or took French or whatever, but if you take out the S, it looks like L'Hôpital's rule. That's usually how I say it. And for you French people that know this, I think there's supposed to be a little mark above the O, but whatever. Okay, I'll normally say L'Hôpital's rule. So if I say L'Hôpital's rule, it's L'Hospital's rule. Okay, there's a guide actually by that name. Okay, it's not meant to be, if you do this math, you end up going to the hospital. I hope that doesn't, you know, end up being the case, but be that as it may, it's called L'Hôpital's rule, and L'Hôpital is, you know, French for hospital, I guess. All right, so what is L'Hôpital's rule? On page 305, what the text has is correct. Okay, so you can put that down. I'm going to give you the Melvin Hom version. Obviously, I like my version, but it's equivalent to what the book has. There's nothing wrong with it. Okay, so I'll just show that to you there, and then I'll give you my version. You can look at it. Page 305, and I think that was enough time for those of you that don't have the book and don't plan on getting it. You can just look at the video later. All right, L'Hôpital's rule involves limits. So we're going back to limits, and the limit is a quotient, something divided by something. Okay, so here's L'Hôpital's rule. If limit as x approaches a of f of x over g of x yields 0 over 0 or infinity over infinity. Okay, specifically, so that means the limit of the top is 0, limit of the bottom is 0. Or limit of the top is infinity, limit of the bottom is infinity. L'Hôpital's rule says the limit as x approaches a of the quotient is equal to the limit as x approaches a of f prime of x divided by g prime of x. That's the essence of L'Hôpital's rule. If you get 0 over 0 or infinity over infinity, take the derivative of the top, take the derivative of the bottom, you will get the same limit. Okay, I'll show you the book's version also in a second, but that's the essence of it. This may be the version you want to put on your next cheat sheet. And a big note, it's actually a nice note, do not use the quotient rule. Do not do the quotient rule here. It's easier than the quotient rule. In fact, dare I say, this is the quotient rule that you would have liked back in chapter 3. You know, if I said, what's the nice way to do the quotient rule, which would have been incorrect, is to just say, oh, take the derivative of the top and the derivative of the bottom. Okay, that's not true for the quotient rule, but for L'Hôpital's rule, that's exactly what you do. To find the limit of this quotient, take the derivative of the top, derivative of the bottom, and you get a new limit. Okay. All right, now getting back to Mr. Stewart, our author, on page 305. Right, so essentially, right there, limit as x approaches a of f of x over g of x is limit as x approaches a of f prime of x over g prime of x. Okay, if you get 0 over 0 or infinity over infinity. And when I say infinity over infinity, notice it could be plus or minus infinity. So it could be positive infinity over positive infinity, which is the majority of the cases. But you could have negative infinity over negative infinity, or negative infinity divided by positive infinity, or positive infinity divided by negative infinity. All of those are fine. Okay? And they even have it right there where it says 0 over 0 or infinity over infinity. Just take the derivative of the top and the derivative of the bottom. Okay. And furthermore, I put x approaches a. It also works for x approaches a from the left, so you might have a minus sign there. You could have limit x approaches a from the right, there'll be a plus there. You could also have the limit as x approaches either positive infinity or negative infinity, same thing. Okay, so they could have x approaches a, or x approaches a from the left, x approaches a from the right, x approaches infinity, x approaches negative infinity. Those are all fine. All right, so as I usually do, I'll just go ahead and give you plenty of examples of those. And let me go ahead and show you the book. Again, for those of you who don't have the book. Okay, so we had to do 9 to 65 odd, 4.4. So let me give that to you presently. 9 to 65. So starting on page 311. Find the limit by L'Hopital's rule, or if there's something easier, use it. Okay. So there's all that. Up to 27. Okay. And we had to go up to 65, I believe it was. So I think this should be focused well enough that you can see it all. Whoops. 63. Yeah, I can't quite get 65 in there. Turn the book a little. Here we go. There's 65. Really holding the book at a funny angle to get this. The bottom has limit x approaches 0 from the right. I can't go any farther up because it's touching the base of the document camera. There we go. All right, so how do you use this L'Hopital's rule? Number 9. Limit x approaches 4 of x squared minus 2x minus 8 divided by x minus 4. Okay, this is 0 over 0. If I plug in 4 on the top, I get 16 minus 8 minus 8, that's 0. And 4 minus 4, which is 0. Okay. So L'Hopital's rule applies. Okay. Equals, and LHR means I'm doing L'Hopital's rule. In case you're saying, how do you go from here to here? LHR means L'Hopital's rule. Okay, so you can use that notation too if you want. So L'Hopital's rule says, take the derivative of the top and the derivative of the bottom. Do not use the quotient rule. Just give me the derivative of the top, 2x minus 2. Derivative of the bottom, 1. Now just plug in, and it's easy. 2 times 4 minus 2, which is 6. Right? Okay. That's the way it works. Okay, 13. A little bit tougher. Limit as x approaches pi over 2 from the right of 1 minus sine x. Okay, now pi over 2 from the right, let me think in terms of degrees. Pi over 2 is 90 degrees. So coming from the right means you're coming from 91 degrees. So the angle is here. It's in the second quadrant. It's a second quadrant angle. So this is supposed to be 91 degrees, even though I've exaggerated a little bit more, but it's coming like 91, 90.1, 90.001, and so on. Right. Okay, cosine of pi over 2 is 0. Sine of pi over 2 is 1. 1 minus 1 is 0. Okay, this is a one-sided limit. So by L'Hopital's rule, take the derivative of the top, same limit, limit x approaches pi over 2 on the right. Derivative of cosine is negative sine, temporarily think of that as negative sine. Derivative of negative sine is negative cosine. So I have negative sine divided by negative cosine. That's why I made them both pluses. Okay, now if I take the limit, sine of pi over 2 is 1. In the limit for the cosine of 91 is a very small negative number. Okay, the x coordinate is a small negative. So 1 divided by a small negative is a large negative. So the limit is negative infinity for that one. Okay, so it's a little bit harder. All right, 19. Here's one where infinity is involved. Limit is x goes to infinity of natural log of x over square root of x. Okay, this is infinity over infinity. Okay, when x gets big, ln x gets big, square root of x gets big. So L'Hopital's rule applies. So I can take the derivative of the top, derivative of the bottom. Again, do not do the quotient rule. Do not use the quotient rule. Just take the derivative of the top, derivative of the bottom. All right, so derivative of the natural log of x is 1 over x. Derivative of the bottom, which is x to the 1/2. 1/2 x to the negative 1/2. Okay, now to clean that up, that x I'm going to slide down. That's allowed from algebra. Right? If you have a fraction on top like that, that denominator can slide down into the denominator of the main. Okay, that's going to come up as a positive exponent. This 1/2 will become a 2 on top. Right? Dividing by 1/2 is the same as multiplying by 2. So that dividing by 1/2 becomes a multiplication by 2. The x to the negative 1/2, I'm going to bring upstairs as x to the 1/2. And this x, I'm sliding down to be x. So now it looks like this. Okay, and now I just combine these. X to the 1/2 divided by x. That's like x to the 1, right? So x to the 1/2 divided by x to the 1 is x to the negative 1/2, which I can write as 2 over radical x. And there it is. Now that limit is equal to 0. Okay. All right, so this is L'Hopital's rule. If you have a limit of a quotient, it's got to be a quotient, something divided by something. And you get 0 over 0 or infinity over infinity. Take the derivative of the top, take the derivative of the bottom, you get the same limit. Okay, 21 is a little bit of a trick question. Limit x approaches 0 from the right of ln x over x. Okay, now I drew myself a little bit of a map, a picture here of natural log of x. When x approaches 0 from the right, ln x drops to negative infinity, right? Ln of a very small positive is a very big negative, negative infinity. And when x approaches 0 from the right, x approaches 0 from the right. So negative big divided by small positive. Do not do L'Hopital's rule. This is not either 0 over 0 or infinity over infinity. This is negative infinity over 0 plus small positive. That's determinant. If you have a large negative and divided by a small positive, you get a large negative. So the answer is automatically negative infinity. Don't do L'Hopital's rule. You'll get the wrong answer, perhaps. Okay. This we can determine. Okay. Large negative divided by small positive, you get a large negative. Okay, then 27 is the next one I was going to show you. This is quite instructive. It's a little bit different. It looks the same. 27. Limit x approaches 0, e to the x minus 1 minus x over x squared. Okay. Again, you should recognize I'm doing problems right off the homework. You should know that by now. All right, x approaches 0. E to the 0, 1, minus 1, 0. minus 0. So the top is 0. Divided by 0 squared, also 0. 0 over 0. So I can do L'Hopital's rule. Differentiate the top, differentiate the bottom. Derivative e to the x is e to the x. Derivative of -1 is 0. Derivative of negative x is -1. All over derivative of the bottom, 2x. Once again, I get 0 over 0. You can do it again. So here's our first instance where you have to do L'Hopital's rule twice. Okay, I think shortly I'll show you one where you have to do it many times. So again, you get 0 over 0. Plug in 0, e to the 0 is 1. 1 minus 1 is 0. Do it again. Derivative of the top, e to the x. Derivative of the bottom is 2. Now I can plug in. Put a 0, e to the 0 is 1. Final answer is 1/2. Okay. All right, 33, a little bit harder. Limit as x approaches 0 of x 3 to the x over 3 to the x minus 1. Plug in 0, the top is 0. The bottom is 3 to the 0, which is 1. 1 minus 1 is 0. So I do L'Hopital's rule. So LHR means L'Hopital's rule. Limit h approaches 0, x approaches 0. Okay, that looks like a product rule. First function times the derivative of x. Recall the derivative of 3 to the x is 3 to the x natural log of 3. Remember that? So again, we don't like bases other than e. They're clumsier, right? Derivative of 3 to the x, 3 to the x, ln 3. Derivative of 10 to the x, 10 to the x, ln 10, and so on. All right, plus second function, 3 to the x, times the derivative of the first, but the derivative of x is just 1. All over the derivative of the bottom, 3 to the x ln 3. Now I plug in 0. So that's gone. That's 3 to the 0, which is 1 on top. 3 to the 0, 1 ln 3. So final answer is 1 over natural log of 3 for that one. Okay. All right, so this is L'Hopital's rule. There has to be a quotient, something divided by something. And if you get either 0 over 0 or infinity over infinity, infinity means plus or minus infinity for both the top and the bottom. Then take the derivative of the top, take the derivative of the bottom, and you get the same limit. Okay, now 41 on the next page is really interesting. I'll show you why. Limit x approaches 0, cosine x minus 1 plus 1/2 x squared divided by x to the 4th. Okay, I've already shown it, but let me temporarily cover it up, but you already saw it anyways. So plug in 0. Cosine of 0 is 1, minus 1 is 0, plus 0, x to the 4th is 0, so 0 over 0. Apply L'Hopital's rule. So take the derivative of the top, derivative of the bottom. Derivative of the bottom is 4x cubed, that's easy, right? Derivative of cosine, negative sine. Derivative of -1 is 0, so forget about it. Derivative of that, 1/2 x squared is just x. Plug in 0. Sine of 0 is 0, negative 0 is 0, plus 0 divided by 0, 0 over 0. Do it again. Okay, derivative of negative sine x, negative cosine x, plus derivative of x is 1, divided by 12x squared. Still 0 over 0. What is 0? Negative cosine 0, that's -1, plus 1 is 0, divided by 0. So do it again. What's the derivative of the top? Derivative of negative cosine, positive sine, divided by 24x. Plug in 0, 0. Still 0 over 0. Keep going until you don't get a 0 over 0. Okay, derivative of the top, cosine x, derivative of the bottom of 24. Finally, I can just plug in. So plug in 0, cosine of 0 is 1, 1 over 24. So here's an interesting example. We had to apply L'Hopital's rule, what, 1, 2, 3, 4 times. But after 4 times, we finally got our answer, 1 over 24. So you might have to do L'Hopital's rule more than once. All right, now for a little bit harder problem, something like 43. Let's go back and look at what L'Hopital's rule said. Okay, the part at the bottom, f of x over g of x, there has to be a quotient, right? Something divided by something. L'Hopital's rule. Quotient, something divided by something. Okay, so the question is, what do I do if I don't have a quotient? If it does not look like that, now then you got to force it. Like 43. Limit x opposed to infinity of x sine of pi over x. That's a product. It's something times something. I need to make it a quotient. So here's a step where you almost would never do this in algebra. We have to now. Okay. So I say to myself, if I multiply by x, it's the same as dividing by the reciprocal 1 over x. Right? So I claim this is equivalent to this. Right? Now, almost always in your algebra, you went the other way. You say to yourself, okay, I got something this weird. Say, oh, if I divide by fraction, I multiply by the reciprocal. But yes, you are allowed to go backwards also. And here's a case where you need to go backwards. Okay, L'Hopital's rule only works if there's a quotient, something divided by something. So this is a product. So what do? I force it to be a quotient, something divided by something. By the way, you say, can I bring this one into the denominator? Yeah, but you don't want to mess around with trig functions that much. All right, so it's better to do that. So multiplying by x is the same as dividing by 1 over x. Is that right? And that's what I'm doing here. Just so I can force it to be a quotient. Now I'll double check. It is 0 over 0. If I plug in a super big positive number, this is like 0, sine of 0, 0. This would be 1 over a billion. That's also 0. So I can do L'Hopital's rule, but before I do that, let's clean this up a little. We want to be ready for taking a derivative. Again, pi over x, pi is a constant. I don't want to do the quotient if I don't have to. Make it pi x to the negative 1. And likewise, make that x to the negative 1. All right, now I'll do L'Hopital's rule. All right, so derivative of sine blah, blah, blah is cosine blah, blah, blah. Cosine pi x to negative 1. I might as well write it the way it originally was, which is pi over x, right? Where'd it go? Pi over x. Cosine pi over x. Then by the chain rule times the derivative of the inside, which is negative pi x to the negative 2. So temporarily think of that as negative pi x to the negative 2. What's the derivative of the bottom? Negative x to the negative 2. The x to the negative 2's cancel out. That negative and that negative cancel, so that's why I changed it to a plus. You can just directly cancel these out. You may say, oh, don't I have to put that on the bottom and that on? Not necessarily. This is the exact same thing as this, right? So if you have w to the 5th over w to the 5th, cancel them out. If you have x to the negative 2 divided by x to the negative 2, cancel them out. You don't have to bring that up and bring that down. They can just cancel. Okay, so this was a negative pi divided by negative 1. I make them positive. So now I have limit as x approaches infinity of cosine pi x times pi. Now we can determine what this is. So plug in a super big number, 1 billion. Pi divided by 1 billion is practically 0. So I have cosine of 0 times pi. Cosine of 0 is 1 times pi. So final answer is just pi. Okay, so here's an instance where you have to force it to be a quotient. There wasn't a quotient in the beginning. It wasn't something divided by something. So we have to force it, we have to make it that way. Okay, let's see. Next one I want to show you. So I know I'm going a little bit out of order here, but just trying to go by difficulty level. 29. That's hyperbolics. Limit x approaches 0 of hyperbolic tangent of x divided by tangent of x. Okay, now hyperbolic tangent is sinh over cos. Okay. You might recall sinh of 0 was 0, so the numerator is 0, so this is going to be 0. Regular trig function, tangent of 0 is also 0. So it is a 0 over 0 case. Okay, so I can take the derivative. Derivative of the top, hyperbolic secant squared. Derivative of the bottom is regular secant squared. It's 1 over 1, which is 1. Okay, so a little bit of a reminder here. Ignore all this stuff I messed up. But sinh x was e to the x minus e to the negative x divided by 2. Cos is e to the x plus e to the negative x divided by 2. And let me try to convince you again that hyperbolic tangent of 0 is 0. Sinh over cos, if you put a 0 right there and also right there, you get 0, right? So 0 divided by 0, so the top is 0. Okay, so there we go. And then let's see, hyperbolic secant is the reciprocal of cos. So it's 2 over e to the x plus e to the negative x. Then if I plug in 0, put a 0 there and a 0 there, you get 2 over 2, which is 1. Squared, you get 1. So it's 1 over 1, which is 1. Okay. Then let's see. Next one I'm going to show you is 49. A little bit harder there. (49) Limit x approaches 1 from the right of ln x tangent of pi x over 2. Okay. Again, right now it only looks like a product. I need a quotient. Fortunately, tangent itself is a quotient. It's sine over cosine. So I don't do the same game as I did before, trying to sneak something in below. Tangent, write it as sine over cosine, and there's a quotient. Now it said limit as x approaches 1 from the right. Well, let's see. I know ln of 1 is 0, so that wipes all of that out. And by the way, tangent of pi over 2 is also 0. Okay, how about the bottom? I plug in 1. I'm taking the cosine of pi over 2. That's also 0. So it is 0 over 0. So L'Hopital's rule does apply, but it's a little bit clumsy. I need to take the derivative of the top, which is a product. Okay, so first function is ln x, second function sine pi x over 2. Okay, so here we go. First function times the derivative of the second. Derivative of sine of whatever is cosine whatever times the derivative of the inside. Derivative of pi over 2, x is pi over 2. Plus second function, sine of pi x over 2, times the derivative of the first. What's the derivative of ln x? 1 over x. Okay, what's the derivative of the bottom? Derivative of cosine of blah, 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 negative sine, blah, 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 times the derivative of the inside, which is again pi over 2. Now, that looks real bad, but it actually isn't so bad after all. Think of what happens when I plug in 1, put in 1 from right. I have ln of 1, which is 0. So that wipes all of this out, right? Right there. Ln of 1 is 0. So forget about the rest. Put a 1 here and here. 1 over 1 is 1. Put a 1 there. I'm taking the sine of pi over 2, which is 1. So the numerator is just 1. Denominator, plug in 1. I have negative sine of pi over 2. Sine of 90 degrees, that's 1. So it's negative 1 times pi over 2, or negative pi over 2. So there we go. So, and the reciprocal of negative pi over 2 is negative 2 over pi. So the final answer is negative 2 over pi. Okay. And let's see, I messed up in my original presentation of 4.455. So let me try to do that right now on paper for you without trying to mess it up too much. What time is it? I'm almost done. Okay, 55. There's a certain trick for that one. X minus ln x. Okay, so let me just write on here. Okay, this is big. This is big. Okay, so what do? I need to have something in the denominator. So here's a trick this time. Go like this. In red, multiply top and bottom by x. And then I split it into 2 limits. Okay, the limit of a product is a product of the limits. Limit x approaches infinity of x. Limit x is approaching infinity of x minus ln x over x, which I'm going to choose to write as 1 minus ln x over x, like so. Which is limit x to infinity of x. The limit is x to infinity of 1 is 1. Okay, so 1 minus limit x approach infinity of ln x over x, like so. That's the key thing. Now I can figure out this limit. Okay, so I have to take a little time out, as it were, and find this limit. So one more time from the beginning, say there's no fraction, force it, divide by x, divide by x. Okay, split this limit out, limit x goes to infinity of x, and break this into 1 minus ln x over x. The limit is x opposed to infinity of 1 is just 1. And this one I'm going to do by L'Hopital's rule. So limit x opposed to infinity of ln x over x equals, by L'Hopital's rule, limit x opposed to infinity. That's big over big. So what's the derivative of ln x? 1 over x. Derivative of x is 1. So now that's 1 over big, that's 0. Right, so now I know that this thing is 0. All right, so time in, getting back in, I have limit x opposed to infinity of x times 1 minus 0. Okay, I now know this is 0. So I have 1 minus 0, which is 1. So 1 times this, that approaches infinity. So final answer is infinity in this particular case. All right, so that's how 55 goes. Okay, folks, I see we're just about out of time. Let me do my focusing thing here. Again, and that's pretty much it for today. So tomorrow I'll continue with L'Hopital's rule, but hopefully start some 4.5 curve sketches. There's that. That. And 55, the one I just did. That. Okay. And let me see, I think that's all I have for there. Okay. All right, so that's going to be it for today, folks. There's no time to do anything else, so we'll just call it a day. So continue with this tomorrow. Yeah, anybody who came late, put yourself in the chat and I'll get you for attendance. All right, have a good day, everybody. See you next time. Bye.